So let us understand the concept of preemption today. Okay, and then we will go ahead. Okay. So preemption. Hello, am I audible?
Yes.
Yes. Okay. Okay. So essentially, this preemption is mainly a concept of 5G. There's this URLLC requirement in 5G. Okay, so the URLLC requirement is that in 1 millisecond round trip delay, you should be able to transmit packets, some packets, not all the packets, some packets called low latency packets or high priority packets. Okay, so you want to transmit this. Okay, so the question is, how do you maintain 0.5 millisecond, whatever, one millisecond latency in this? Okay, how do you do this? Okay, so how does a typical setup work? In a typical setup, you allocate resources to different users for a given slot and you transmit them. Okay, suppose you have two queues. One is called high priority queue. This is a high priority queue or a low latency. Just 1 minute, sorry. High priority queue, and there's this normal priority. Okay, so the normal priority, what happens? Maybe for this particular slot, if slot these are the slots: slot 1, slot 2, slot 3. Okay, so in slot 3, you are now in slot 3. So essentially, the users must have come and you must have done some processing for them. Make sure that the allocation is allocated and other things beforehand. And in 3, what you do, you fill up the slot. If you fill up the resource grid in 3. This resource grid you fill up. Okay. Okay. So high priority packets, what happen? Whenever they come, you should process them. Okay. So high priority packets are low latency packets. So later you cannot keep them in the queue, make them wait for a few slots. If you make them wait for a few slots, then automatically you will violate the latency constraint. Okay. So effectively, you should process them as and when they come. Okay. But this poses a problem. Okay. See, the problem is, sorry, this one. Okay. So suppose this is your resource grid. Okay, this is your resource grid. This is the frequency. This is the time. Okay. Already a normal user has been allocated these resources. Okay, the top resources have been allocated to the normal. These top resources have been allocated to the normal. Okay, when you're doing this, suddenly a low latency packet came. Okay, when you're filling this up, a low latency packet came, and you have to transfer in the next slot. Okay, so maybe if there is space, maybe you can allocate the user. You may allocate the user. One of the low latency packet guy you can allocate here. Maybe. Okay. Maybe some other packet, you might have to allocate it like this. Okay, this is a low latency packet. Okay. But then what happens when this happens? What is happening is you are actually removing the data from the normal user and putting the low latency data there. Yes. Okay. So for the normal user, what will happen? All other symbols are correct, but these particular symbols which have been overwritten are wrong. Okay, they are overwritten, which are overwritten are wrong. Okay, the low latency user will have no problem because the low latency user will decode this part and be happy, but the normal user will suffer. Okay, so how we have to indicate to the normal user, hello user, sorry, I have to overwrite some of your symbols with a low latency data for some other user. You have to please neglect some parts of it will be wrong. Okay, you have to tell him. So what are the possible scenarios that might happen? Well, let's understand the possible scenarios. For the normal user, maybe these things occupy only few bits. Okay, he may be able to decode with the help of LDPC. He may be able to decode these parts also. Okay, might be. If that happens, it's very good. If that doesn't happen, what will happen? You are going to send, he's going to keep this entire thing in a soft buffer. Next time you're going to retransmit. Whenever you're retransmitting, he's going to add. In the next time, you may not transmit the low latency. You may not transmit the low latency. You will transmit only the normal user data. He'll try to combine them to get SNR and decode them. Okay. The problem is that when you combine data like that, that's called chase combining. So that's called chase combining in hybrid ARQ. Okay. When you do chase combining, what you expect is you expect the data to be the same across two symbols. I mean, across two transmissions. But in this case, it's not the thing. So you have to indicate to the UV saying that please discard your older data. Okay, you dotted data and use the newer retransmission. Okay. So there are some flags in DCI format 1.1. I think DCI format 1.1. DCI format 1.1 to enable this. Okay, called flush flags, where you can flush some part of the older transmission can be flushed, and the newer the retransmission can be taken by the UV. Okay, this is one way of enabling preemption. Okay, essentially, you are creating some hole in the existing users for low latency data. Okay, so this is one way. So there's another way using format DCI format 2.1, which is a little bit more complicated. I'm not going to go through that, but there's one more way which is a little bit more concrete. Something of similar ideas only, again based on preemption. But how you tell the user which data is correct and which data is not correct. Okay, so you just keep this idea of preemption in mind. Keep this idea of preemption in mind that for low latency, whenever the packet comes, you have to serve it. Whenever data for the low latency user comes, you have to serve it. You cannot wait for the next empty slot where you are going to fill his data. Okay, so when you're doing that, you are going to overwrite the data of the existing users. So you have to indicate to the existing users, sorry, we have overwritten your data. Okay, is this concept clear? Hello.
Yes.
Yeah, is this idea clear? Okay. So, I mean, there are a lot more details on this preemption on the DCI format 2.1. DCI format 2.1 has a lot of stuff on this preemption and how you do this and other things. Anyway, the basic idea is the same. I mean, I don't want to get into the very, very fine details of that preemption at this moment. Okay. If there are no questions, we'll move on to power control, uplink power control. Okay, that. Okay. So now let's look at uplink power control. Okay. So just before we start, I mean, so generally all the handsets that we have are power class 3 handsets. Now, power class 3 handsets operated, the average transmit power is 23 dBm. Okay. So remember the difference between average transmit power and the peak transmit power. So average transmit power means essentially the power average over certain time interval. I mean, that's part of the specification. Are the people this is regulatory are regulatory constraints will be there on how much time you average now. Okay, so all your handsets are 23 dBm. I mean, mainly because of SAR restrictions. Okay. So why is so in general, see earlier when during the time of CDMA and other things, there used to be a lot of downlink power control also. In downlink power control, essentially they used to change the power per UV so that the chips and other things add up correctly. Okay, but from the advent of LTE, in LTE generally you don't do downlink power control for different users, mainly because already the PAPR of the signal is high. You are backing off in the base station. On top of that, if you do unequal power allocation across all the users in the downlink, that will lead to a very much higher power difference and higher PAPR. And that will degrade the entire system performance. So in general, more or less, all the UVs in the downlink are transmitted at equal power. There's a small difference between the different channels. Again, that's all left to implementation. But it's not so, I mean, it's not the dynamic range of power across users and across different channels is very, very less in the downlink. Okay, so effectively there's no downlink power control. Okay, there's some minor stuff that that are there, but we can, for all practical purposes, we can think that it's almost constant downlink power. Okay, mainly for this OFDM. I mean, this is for the issue of the OFDM. So uplink power control, on the other hand, is absolutely required. Why do we require uplink power control? First of all, let's discuss those points. Okay. So what might happen? So users are distributed all across the cell. Okay. So what we want is, we want to at least try to get enough power from faraway users and not too much high power from users which are close to the base station. Okay. So you want to maintain some balance of power in certain range so that your receiver can demodulate it. At the same time, you are not overwhelming or saturating your receiver at the base station. Okay, so you want to do that. That's one thing. And second thing is, you also want to make sure that the interference caused by UVs across cells is in some sense minimized. Okay, so you want to do both of this using uplink power control. Of course, the major problem of this uplink is that you cannot go on transmitting just because you are far away from the base station at the cell edge. You cannot transmit more than 23 dBm. Still, you have the 23 dBm constraint. Okay, you have the 23 dBm constraint. Okay. So at this point, I just want to mention one small point. See, when you look at a GSM phone, that's a 2G phone, they typically transmit much more higher than 23 dBm. Okay, they transmit actually about almost close to 1 watt of power, which is 30 dBm. Okay, but the duty cycles, the amount of time that they transmit 30 dBm, when you average over the duty cycle, it becomes less than 23 dBm. Okay, so all of us should understand that 23 dBm is not a peak power, but it's average power over time. Okay, that's very important, particularly in systems like OFDM, where there's a lot of PAPR. Instantaneously, you'll always cross 23 dBm. Okay, if you don't want to cross 23 dBm even on the peak power, then your average transmit power will be about 13 dBm, which is very low. Okay, so in general, you'll be crossing on peak power with power.
Hello, sir. Your voice is not audible, sir. Hello.
Hello. Hello. Am I audible?
Yes,
When
yes, sir.
did you lose
Yes.
me, please? I have been talking from last 10 minutes. So when did you lose me?
Just, sir, one minute ago, just.
Okay, 1 minute ago. Okay. So essentially, what I was trying to say is, last minute what I was saying was that you require power control to maintain some amount of power at the base station, receive power at the base station, so that your SNR or SINR is good. I mean, we focus on SINR is good. And you also want to make sure that you have power control so that you don't cause interference to the other users also. Okay. So there are two ways of doing uplink power control. One is called the open loop mechanism. So in the open loop mechanism, essentially what does the UV do? The UV tries to estimate path loss, essentially the loss between what the base station transmits and what you receive, and try to compensate that. Okay, just in the open loop, you try to compensate. Okay, as much as possible. And then there's the next thing is called the closed loop mechanism. So on the closed loop mechanism, what you do is the UV tries to compensate something of the path loss. Then the base station sends a feedback saying that, hi, I'm not receiving too much. I'm receiving lower power. I'm receiving low power. So the UV is asked to increase its power. Or the base station is receiving a higher power, the base station will ask the UV to reduce the amount of power it has. Okay. So based on this mechanism, you try to maintain some kind of equilibrium so that you get good SNR for the UV. Okay. Is this two mechanisms clear? We will discuss this a little bit going forward. Any questions before we proceed? Okay. Okay. And one thing that we should understand is for all the uplink power, there are multiple channels in the uplink: PUSCH, PUCCH, PRACH, and SRS. Okay, so there is separate power control mechanism for all these channels. The only constraint is that the total power that you allocate across all the channels is upper bounded by 23 dBm, the PC max for power class 3. Okay, it's independent power channel. Okay. So, so this is a general guiding principle. But of course, there are lots of exceptions to all those things. We don't have to go into all those things at this moment. So, in principle, all the physical channels are separately and independently power controlled. Okay. Of course, there's a lot of exceptions to this. Let's not worry about them. So, in general, PUCCH and PUSCH have high priority. First, the PUCCH is assigned power determined by some algorithm, and the remaining power is allocated to PUSCH. Because until you decode PUCCH, you cannot decode PUSCH. Okay, because HARC and other things are there in the, this HARC acknowledgements and other things are there in PUCCH. But PUCCH, you should understand, is a very, very small channel. So, effectively, a lot of power is allocated to PUSCH. Okay. So, what this says is the amount of power, forget about the summation, this is across multiple carriers. So, the power you allocate to PUSCH is upper bounded by what is the maximum power minus the power that's allocated to PUCCH. Okay, the remaining power is scaled across all the other channels. Okay, so effectively what I want to try to say is different channels have different power allocation strategies. There's a priority across different channels, and you assign powers based on some priorities. Okay. So now let's understand what is the power control for PUCCH. Okay, this is the first push power control. Okay, so let's think about this. So PUCCH has multiple different formats. We saw format 0, we also saw format 2. There are other formats like format 1, format 3, and I think format 4 is also there. I think so. Format, okay, yeah, other formats are also there. Okay. So each of this format has a different way of demodulation. For example, format 0 is a waveform based demodulation. On the other hand, format 2 is QPSK based with something else. Format 1 has some other thing. So each of these channels will have a certain SINR requirement, signal to interference noise ratio requirement, okay, for them to be decoded reliably. Okay, so all the channels are not equal. Format 0, on the other hand, format 0, for example, can be decoded at a low SNR, whereas format 2 may require a little bit higher SNR. Okay, so the amount of the SNR, SINR required to decode each channel is different. Okay, so you have to keep this in mind. So essentially, the goal is to achieve a desired error rate. There's some specification I forgot, 10 power minus 3 uncoded or some 10 power minus 6 coded or something like that. Okay, so it depends on SINR that you receive, and each of the PUCCH formats have different requirements. Okay. Okay. So to achieve this, what they do is they have something called a target receive power. That's called a P0 PUCCH. That's a target receive power that's broadcasted as part of the SIB messages. Okay, so they say that we want to receive this much PUCCH power. Okay, this is the base level power. Okay, so and what they do is for each format, they added a correction factor for each format. This delta format is there now that changes with different format. Format 0 will have something, format 1 will have something, format 2 will have something. Okay. So for example, format 1 with BPSK will have 0 dB. Format 1 with QPSK will have an offset of, it requires 3 dB more. Format 0 will have a different thing. Okay. So this delta format that's format dependent. Okay. So P0 PUCCH is the base level power that's required. On top of that, you change it for each format. Okay. And this is the correction factor for, so P0 PUCCH is transmitted in the, in the RRC parameters. Delta format, anyway, you will know because you know what is the format that you are sending. So you can apply that correction factor in the uplink. PLDL is the path loss in the downlink. Okay. So essentially, you would try to say that the path loss in the downlink is equal to path loss in the uplink, which is almost correct. Okay. So basically, based on SSB or something, the UE estimates the path loss in the downlink. Actually, using PSS in the SS block, it estimates the path loss downlink. And you are trying to compensate for the entire path loss for PUCCH. Okay, so essentially, you add that power so as to compensate for that. Okay. And then finally, delta is the closed loop correction factor. We'll come to delta later. Okay, so this is the target. P0 PUCCH plus delta format is the target. Sorry, is the target. And PLDL is the compensation for the path loss. So this much power you have to transmit. Okay, but the problem is you are constrained by your 23 dBm. PC max is 20. PC max is the, for each power class, what is the maximum power? If it's power class 2, it's 26 dBm. Power class 1, it is 29 dBm. Okay, but generally all our handsets are power class 3 handsets, okay, which is 23 dBm. So you 23 dBm minimum of 23 dBm comma this summation. Is this clear? That is the power that you are going to use for PUCCH. Is that fine? Any questions before we proceed?
Sir, if the second part is having a larger value, then the path loss won't be compensated, na?
Yes, it won't be compensated. So, for example, this comes as 28 dBm. For example, P0 PUCCH plus PLDL plus delta format comes at 28 dBm, for example. Whereas PC max is 23 dBm, but you have to constrain on 23 dBm. So automatically, then your SNR that you receive in the for the PUCCH channel will be lower by 5 dB than what you require. Okay, there's nothing you can do because you're upper limited by the constraint of 23 dBm. Okay, but generally what you do is you design your PUCCH channel that for a given cell size, P0 PUCCH plus the approximate path loss plus delta format will be less than PC max. So you do cell dimensioning now. Based on the cell dimensioning, you can you make sure that you're generally close to PC max or a little bit less than PC max. You have to do that. And generally P0 PUCCH channels, what happens is are generally designed for they operate at very, very low SNR. Okay. Okay. Then what is this delta? So delta is the closed loop correction factor. So now, first of all, first you transmit with delta is equal to 0. Okay. Then the base station gets certain power. Then the base station sees if it's able to decode the PUCCH. If it's able to decode the PUCCH, it will say nothing. It won't do anything. But on the other hand, if it finds that you are transmitting at very high power, what it will do is it will send delta to be -1 in the next DCI format. Okay. Then you will put delta is equal to -1 and reduce your power. On the other hand, if it's low, if the receive power is low, it will ask you to increase the power by +1 or +3 dB. Okay, so this delta can take 4 values: -1, 0, +1, and +3 dB. So you require 2 bits of information will be transmitted in the downlink scheduling assignment. Okay, for the uplink, it will transmit. It will transmit that. Okay, so that is the closed loop correction factor, whether it will increase or decrease or how you want to do your power control. Is this clear? Of course, all of this is constrained by the fact that you cannot transmit more than PC max.
Excuse me, sir. If the user is moving, then this delta will keep on changing, so it won't reach any stable value. Then
Yeah.
what will?
So essentially, this delta is not always transmitted. So the base station will have some. It's not transmitted every slot. Okay. So see that this delta also has steps. Not -1, 0. It's not very fine. It's in steps. So it will wait for some time, and if it really crosses the threshold, only it will change the delta. Okay. So that is a part of the implementation, how fast you want to change your delta. You cannot also go on changing your delta every millisecond. Okay, that will cause problems in your power amplifiers and other things. Okay, so you'll have a smaller loop. The loop time will be larger. Okay? That's part of the implementation. Okay, any other questions? So now let's look at the PUSCH. Okay, so generally one thing that you should remember is PUCCH channels are very, very small channels. I mean, they occupy 1 or 2 RB. I mean, RB2, few RBs, not more than that. Couple of RBs. Okay, With PUSCH can be larger, much more wideband channel. Okay, so the formula for this will be a little bit different. Okay, let's look at the formula first, and then we'll understand other things. Okay, so the first thing is you see that it's PC max minus PUCCH. So already you have used some power for PUCCH, so you subtract off that power from PC max. Okay, that is the maximum power that you can transmit PUSCH channel with. Okay, then you have a certain formula. Again, there's a target P0 PUSCH. Okay, per RB, how much is the power that you require? Okay, so this P0 PUSCH is mentioned in terms of RB. Each RB, how much power you require. Okay, and so if you have like 1000 RB, I mean not 1000 RB, if you have 100 RB, then you add a factor 10 log 10 M. Essentially, this is a bandwidth. So this is the bandwidth in terms of RBs. Okay, so this is the basic power, and you're multiplying with the number of RB, so that to get total power that you require for that particular user in that across that band. Okay, I mean we are putting this in dB, that's why it becomes P0 PUSCH plus 10 log 10 M. Otherwise, in the normal domain, non-dB domain, with multiplication of M with P0 PUSCH. Okay, that's one thing. So this, I mean, okay, that's one thing. A second thing that you see is, of course, is delta MCS. What is delta MCS? Again, uplink also can send multiple formats depending upon your MCS. What is, for example, if you are transmitting QPSK with rate half, you have a certain what do you say? You have a certain SNR requirement. On the other hand, if you are transmitting 64 QAM, you have a different SANR requirement. Similarly, for 256 QAM, you have a different SANR requirement. So this delta MCS depends on the particular modulation and coding scheme that you use. Okay, so this is called the correction factor, delta MCS. Okay. So similar, very similar to like here it's called the delta format. Here it's called the delta MCS. Okay. But one interesting thing you see is here you're compensating for PLDL completely, the path loss. Here you are compensating for alpha times path loss. Okay, so alpha is some factor that is less than 1. Okay, this is called fractional power control. Okay, so in PUCCH you do something called full power control. Okay, so full power control means you try to compensate for the entire path loss by putting PLDL. Okay, you are compensating for that. Here, what you are doing, you are compensating only a fraction of the path loss. You are multiplying by a factor alpha, which is given by the base station. Okay, and you are compensating for the for this fractional path loss in the uplink. Okay, why do they do that? Why do you do that? Can anyone tell me? Why are you trying to compensate only for a fraction of the path loss and not full? See, what happens is, so every user, for example, so this, I mean, so this is PUSCH occupies a lot of larger bandwidth also. No? So if multiple users are transmitting, okay, in a cell, so everyone tries to compensate for their path loss. If everyone tries to compensate for the path loss, exactly, what happens is you can show that the inter-cell interference increases. For example, there's a UE at the cell edge, close to the cell, okay, that is shared by two base stations. Okay, so you are trying to compensate the power to your attached base station, okay, by increasing the transmit power. When you're doing that, you're also causing interference to the neighboring base station. Yes, it turns out you can show this theoretically, I mean, using stock geom and other things, that if alpha is equal to 1, then the amount of interference in the system actually increases quite a bit and your overall system performance degrades. Okay, so in general, what you do is you don't try to compensate for your entire path loss. You try to compensate only a fraction of your path loss. Okay? So how the value of alpha is chosen and other things, there are a lot of theoretical results on that. It depends on your path loss exponent and other things. Based on that, you can choose your alpha. Okay, so this is called as the I mean, so that's why you do what do you say, fractional power control for the PUSCH in the uplink. Okay, is this concept clear? Did you understand why they do fractional power control? And of course, the other part is, of course, I mean, fractional power control also helps you to save your battery, because you're not trying to compensate for the entire, uplink path loss. Okay. So any questions on this? Do you understand this concept of fractional power control?
So this fraction value will be estimated by the UE itself, or base station?
So base station will indicate how much is the alpha that you should send. Okay, this alpha is a parameter that's sent by the base station. I can tell you which RRC parameter also. Let me find out that one. Excuse me. Okay. And of course, this delta. This delta is exactly like the PUCCH delta. This is the closed loop power control. Okay? Closed loop power control to make sure that enough power is received at the base station. Okay. So what I'm telling is a very, very simplified view of what happens. Actually, it's a little bit more complicated across how things are done across channels. There's also more split across different formats and other things. Okay. I mean, but it's good to understand. I mean, those of you interested can read those those very specific details. But what I want you to understand is the high-level overview of how power control is done. Okay. So if you just take the two channels PUCCH and PUSCH, first you do PUCCH, you compensate for the full path loss. That's mainly because the bandwidth is very, very low and the amount of power you require is also low. Okay. And then you come to PUSCH, where you do fractional power control and you allocate the remaining power. After you allocate to PUCCH, whatever is remaining, you allocate to PUSCH. Okay? Did you understand how this power control? So this power control mechanism happens across all the UVs. So what happened? That's why sometimes you put your phone, you are using data, and you put your phone in your pocket, or you put it in some closed environment. It starts getting hot. The main reason is the power control loop kicks in, and this delta becomes positive, and it tries to transmit at 23 dBm. Okay, that's why it becomes a little bit more hot also. Sometimes you can see that phenomena. Okay, so it's better not to close your phone with hand or put it in your pocket in general, so that at least you'll save your battery. Okay, so that's what I want to tell about power control, uplink power control.
Sir, could you please explain those plots?
These plots, okay. So there's just an example of how you do. See this, 1 minute, let me tell you. So this red line, I think this red line is the actual power, path loss. Okay. This blue line is fractional power control. Okay, so you're not compensating for the entire path loss, I think so. But trying to compensate only fraction of it. So essentially alpha times path loss. Okay, so alpha is less than 1, so the slope is less. Okay, so because you're doing that, the receive power also will be less. Okay, that's what it means. Nothing more than that. Okay, good. So at this point, I'll stop. Next class, you guys have to tell me what you want me to teach on Friday. Saturday, we'll have a class on Friday. Saturday, I'm driving, so Saturday we cannot have a class. We'll have one class on Friday.
Excuse me, sir. Then the receive power should be less than the red line, na? Why it is going up that dotted line?
So because of these other constants are there, na? P0, PUSCH and other things. So it's not starting at 0. I can maybe I'm also not very clear on why this. I'll get back to my Friday. I'll discuss this part. Okay, I'm not very sure on why that is.
Okay.
I think there's some offset because of these other things. Yeah. Good. So we'll stop the class today. We'll again meet on Friday. Okay. Friday, please let me know what you want me to cover, or we can revise some things. And then what I will do is, either if you don't tell me something, I will choose one topic and explain on Friday. Okay. So thanks everyone. Thank you.
Sir, for the assignment, sir, I needed some time.
So okay, for the which assignment is this?
So today is the last date.